Diffraction is a characteristic of waves, and the term refers to the bending of waves as they pass through a barrier. Now, since light is a wave, it's an electromagnetic wave, we expect light to exhibit diffraction. And light does this when you pass it through a slit. Okay, the pattern you observe is called a diffraction pattern for the light. And exactly what does this mean? Let's imagine you were shining a laser pointer at the wall. You might see a spot because of that laser pointer there. Okay. Now imagine that beam of light from your laser pointer passes through a very narrow slit. What you'll find is this spot on the wall is going to spread out. Okay. But in addition to that, you are going to see additional spots around that main spot, okay? And in between those spots is just darkness. So you get this, you might see something like that. I'm not drawing it as well as I could, so let me go to Google. Let's do a Google search for single slit diffraction so you can see what it looks like. So if I do a search for single slit diffraction with a laser pointer, here's some images you might find. This is really neat right here. So here, right here is the main spot, and there's some two spots on the side that you see. Okay, two bright spots, and then in between those spots you have dark areas. So that is what we call the diffraction pattern. Notice that this one right here, this one represents the slit size. So a wider slit versus a very narrow slit. So a narrower slit would cause your spot to spread out more. And this is the one that you see for a green laser pointer. Okay? Alright. So how do we explain diffraction? Why do we get those bright spots and why do you get those dark spots when in a diffraction pattern? One thing to know is that when waves are bent, they emerge at different points. The waves that emerge at different points could end up being out of sync with each other. And so when they end up being out of sync, we say they have destructive interference, and that would lead to dark spots. And now, at certain angles, there are some cases where you have waves doing what's called constructive interference. They sort of reinforce themselves and reinforce each other, and so the bright spots in the diffraction pattern would be something that we would say is due to constructive interference. Now, where the constructive interference occurs depends on the wavelength of the light. Okay, so for example, let's imagine you have a slit, okay, with a 10 to the negative 6 meters slit. So that means the distance d. Okay, I'm gonna just blow it up. Okay, right here. Oops. Okay, so let's make my slit, let's just emphasize the difference there, to be 10 to the negative 6. Okay, so this slit size d is 10 to the negative 6 meters. So that's the distance from one end of the slit to the other. So let's say you've got light coming into the slit from this side. Okay, so let's say it gets bent. So let's look at the light that's bent at this angle theta. So we have theta right here, the angle. Okay, so you have two parallel waves emerging at angle theta from this slit. Okay, now when do you get constructive interference? You get constructive interference if, okay, imagine a perpendicular line over here. When the wave that comes out of here, let's see, what color should I use? Let's just use green right here. This wave right here and this wave right here are in sync. So where this peak happens is at the same distance right there. Okay. That constructive interference happens if this extra distance that the wave down here has to travel, this extra distance here, okay, that extra distance is just d, this d right here, times the sine of theta. You can do the math there and you can find that that extra distance is d. Okay, so when that extra distance is an integer multiple of lambda, so it's equal to 1 lambda, 2 lambda, 3 lambda, and so on. So that is That's how you can determine the angle, okay, where constructive interference occurs. Okay, so for example, if your wavelength, let's say our wavelength is 500 nanometers, that's green light, and your slit size d is 10 to the negative 6 meters. Let's verify that this angle is actually going to end up being 30 degrees. So what do? You can say constructive interference happens when d sine theta equals n lambda, and so we're going to say for n equals 1, okay, this can happen different multiples. You can have 1, 2, 3, and so on. So when n equals 1, you have d sine theta is equal to lambda. Okay, so you can say sine theta is lambda over d. So let's calculate that. Lambda is 500 nanometers, so 500 times 10 to the negative 6 meters, divided by the slit size d, and d is, what's your slit size? 10 to the negative 6 meters. Oops, nanometers, so that's 10 to the negative 9 meters. Okay, lambda is 500 nanometers, so that should be 10 to the negative 9 meters. And so 500 times 10 to the negative 9 divided by 10 to the negative 6. Okay. 500 times 10 to the negative 9 divided by 10 to the negative 6. That should be about 0.5. Okay. Sine theta is 0.5. And inverse sine, that's 30 degrees. Okay, so inverse sine or arc sine of 0.5, that's your value of theta. That's a 30-degree angle. Okay, you can see the angle at which constructive interference occurs depends on the wavelength and the slit size. So you can use this, in fact, this information to determine wavelengths of the different colors of light. Okay, so this is how you come up with numbers for color, a way to measure color.